Hi students, good morning. I am Srinivas, lecturer in chemistry, having 32 years of experience in teaching IIT-JEE advanced and NEET classes. This is a part of second year intermediate physical chemistry or CBSE plus 2. The topic name is solid state. In today's class, we will discuss some part of the solid state, and the subtopics that I already mentioned on the board will discuss in detail about all these parts. The main three physical states are solids, liquids and gases. And we all know the force of attraction between the particles in gaseous state is minimum, and the force of attraction between the particles is maximum in solid state. What is to be discussed in solid state? These are the subtopics, students. First one is lattice points. Second one is the contribution of the particles. Third one is unit cell. And fourth one is types of unit cells and effective number of atoms. Relation between A, where A is the edge length of the unit cell and R is the radius of the particle. So, relation between A and R in different unit cells and calculation of packing fraction. So, the first part is lattice points. What is meant by lattice points? We all know in solid state the particles are closely packed. Among all three physical states, the particles are closely packed in solid state. Still, so much space in solids is vacant. What it means? In some parts of the solid only the particles are present. The space where the particles are present are called as lattice points. See, it's clearly shown on the board. The three different balls, different colors marked in that cube. This red ball means red part. This lattice point is called as body corner. And the yellow positions are called as phase centers, and the white space is called as body center. In addition to these three, one more is also present. This is what is called as the edge center. So, in most of the solids, in these four places only the particle may be here, that may be an atom, that may be an ion, or that may be a molecule. Atoms or ions or molecules are mainly placed in these four places. One more time, listen me students. One is body corner, second one is phase center, third one is body center, and fourth one is edge center. And clearly it's shown that what is the body corner position and what is the phase center, what is the body center and what is the edge center. These four places are called as lattice points. Next one is contribution of the particles. Before that, one point will mention what is meant by unit cell. Unit cell is the smallest portion of an ionic crystal which repeats again and again and represents the entire crystal in all aspects. And it's nothing but the sample piece of the entire solid. I'll repeat one more time. Unit cell is the smallest portion of an ionic crystal, repeats again and again and represents the entire crystal in all aspects. What it means? In all aspects means in the shape, in the properties, everything The unit cell represents everything of an ionic crystal. Before that, types of unit cells, now we will see the contribution of the particle. See students, here the particle is present at body corner. Is this body corner particle is confined to one and only one unit cell? No. In an ionic crystal or in an ionic solid, the body corner particle is shared by a total of 8 unit cells. And this particle, the particle which is at the body corner, it is not confined to one unit cell. It is shared by a total of 8 unit cells. So, the contribution of this particle for one unit cell is 1 by 8. See this. See the corner particle. The corner particle is shared by a total of 8 unit cells. So, for one unit cell, the contribution of that particle is 1 by 8 only. Similarly, the particle which is at edge center, is shared by a total of 4 unit cells. So, the contribution of a particle which is at edge center for one unit cell is 1 by 4. The particle which is at face centered particle is totally shared by 2 unit cells. So, its contribution for one unit cell is 1 by 2. And body center is to one and only one unit cell. It is confined to one unit cell only, no sharing with other unit cells. One more time listen me students. The 4 lattice points, one is body corner, second one is edge center, third one is face center, and fourth one is body center. These particles not confined to one unit cell. These particles shared by so many unit cells in that solid. Based on that, we can calculate the contribution of the particles. See the body corner particle, that is common for 8 unit cells. What it means? Shared by 8 unit cells. So, the contribution of one particle which is at body corner is 1 by 8 for one unit cell. And similarly, the particle which is at edge center is shared by 4 unit cells. So, contribution of one particle for one unit cell is 1 by 4. The particle which is at face center is shared by 2 unit cells. So, contribution for one unit cell is 1 by 2. And the particle which is present in body center confined to one and only one. So, this contribution of this body centered particle is 1 for every unit cell. This is the most important thing, the contribution of the particles at different places in the solids. Next one is types of unit cells. And we already mentioned what is meant by unit cell. Unit cell is, one more time, unit cell is the smallest portion of an ionic crystal which repeats again and again and represents the entire crystal in all aspects. That is what is called as a unit cell. What are the main types of unit cells? In our portion, for an IIT or for NEET or IPE or CBSE second year, these 3 are included in the syllabus. First type is simple cubic unit cell. This is also called as primitive unit cell. Simple cubic unit cell is also called as primitive unit cell. And second one is FCC. FCC full form is face centered cubic lattice. FCC full form is face centered cubic unit cell. BCC is nothing but body centered cubic unit cell, and fourth one is end centered cubic unit cell. So, the different types of unit cells are, first one is simple cubic unit cell, which is also called as primitive unit cell or second one is FCC. The full form of FCC is face centered cubic unit cell. Third one is BCC, body centered cubic unit cell, and fourth one is end centered. When the unit cell is called as simple cubic, when it is called as FCC, when it is called as BCC, and when it is called as end centered. Now we will discuss that. Coming to simple cubic unit cell. See this cube here, which is on the board. The particles are only at body corners. Face center is vacant, edge center is vacant, body center is vacant. In any structure, if the particles are only at body corners, then that unit cell is called as a simple cubic unit cell. See, in any cube, how many body corner particles are present? Totally there are 8 body corners. See, 1, 2, 3, 4, 5, 6, 7, 8. In this, particles occupies all the 8 body corners. If particles are present only at body corner, then that unit cell is called as simple cubic unit cell. The remaining 3 lattice points are vacant. That is, edge center is vacant, face center is vacant, and body center is vacant. And next type is FCC, face centered cubic lattice. See, where the particles are present. See the diagram. The particles are at all body corners and also the particles are at face centers. And in the just now only we mentioned total body corner particles are 8. Total body corner particles are 8 and there are 6 faces for any cube. Face center particles are 6. Of course, particle may be at all 8 body corners or maybe some body corners only. That is what are called as the defects in the solids. That we will discuss in the next classes. Particles in body corner and face centers. Total of 8 body corners and total of 6 face centers. Particle may present in all body corners and all face centers or maybe some body corners and some face centers. But if particles are at body corners and face centers, then that unit cell is called as FCC unit cell, or we can, the full form of that is face centered cubic unit cell. Now coming to the third variety, BCC. See the diagram, it clearly indicates that red particles are at body corners and white is at body center. So, if the particles are at all at body corners and body center, then that unit cell is called as BCC, body centered cubic unit cell. See, the one in which the particles are present in body corners and body center, then only that unit cell is called as body centered cubic unit cell. And the fourth one is end centered unit cell. See the diagram here. Whether it may be in simple cube, whether may be in FCC, maybe in BCC or in end centered, body corner is must. In addition to body corner, if particles are at face centers, then it is called as FCC. In addition to body corner, if particle is at body center, then it is called as BCC. In addition to body corner, see only two phase centers of 6, only two phase centers, that too opposite phase center. The particle should be any two opposite phase centers. What it means? Maybe these two, or maybe these two, or these two, maybe these two. Anything it can be. Not any two phase centers. It's not any two phase centers. It is any two opposite phase centers. So, if the particles are present at body corners and any two opposite phase centers, then that unit cell is called as end-centered unit cell. So, these are the main four types of different types of unit cells. One more time I will repeat. The first variety is simple cubic unit cell, and other name of this is called as primitive unit cell. In this, particles are only at body corners. Second variety is FCC, or face centered cubic unit cell. In this, particles are at body corner and face centers. And third variety is BCC, particles are at body corners and body center. And fourth, end centered cubic unit cell. In this, particles are at body corners, and don't forget, this is very important, body corners and any two opposite phase centers, then it is called as end centered cubic unit cell. So, coming to the next part, effective number of atoms, which is represented by a letter Z. What it means? I already told. Here the particle is at body corner. This particular atom or ion or a molecule is not confined to one unit cell. It is not confined to one unit cell. What is the contribution of this particle for unit cell is nothing but effective number. Any body corner is shared by a total of 8 unit cells. So, contribution of each body corner, each particle at body corner for one unit cell is 1 by 8. That is what we discussed in the second slide, the contribution of the particles. So, for one unit cell, one body corner atom, the effective number is 1 by 8. What it means? The contribution of one body corner particle is 1 by 8 for each unit cell. Totally, how many body corner particles are there? There are 8 body corners. Each body corner contribution is 1 by 8, all 1 by 8. So, effective number of atoms, which is represented by Z, for simple cubic unit cell is 8 into 1 by 8. So, Z value for simple cube is 1. One more time, students. Now we will calculate effective number of atoms. And what it means? The actual contribution of particles per one unit cell. And that too here we are calculating simple cubic unit cell. And we all know simple cubic means particles are at body corners. The body corner particle is contribution is 1 by 8. How many such body corner particles are there? Totally there are 8 body corners, and for each particle contribution is 1 by 8. So, effective number of atoms in simple cubic unit cell is 1. So, the Z value for simple cube is 1. Coming to FCC, how to calculate effective number of atoms? That is Z for FCC. See, simply are where the particle is located, how many such particles are there, and what is the contribution of that particles. We all know particles at body corners. Particles are at body corners and particles are also at phase centers. How many body corner particles are there? See the diagram, it clearly indicates there are 8 body corners. And what is the contribution of body corner particle? And we all know, we discussed it just now, 1 by 8. So due to these 8 body corner particles, the contribution is only 1. Coming to the phase center, there are 6 phase centers. All 6 phase centers showed clearly 1, 2, 3, 4, 5, 6. And each phase center particle is shared by 2 unit cells. So contribution of each particle for phase center is 1 by 2. So 6 into 1 by 2, 3. So contribution due to body corners is 1. Contribution due to phase centers is 3. So the Z value for FCC is 8 into 1 by 8 plus 6 into 1 by 2. So that total is 4. So Z for FCC, effective number of atoms per phase centered cubic unit cell is 4. Now coming to BCC. It's very clear. This is the unit cell of BCC. Particles are at body corners and also body center. Simple. What is Z value? Z is equal to how many body corners are there and what is the contribution of the body corner? 8 body corners and contribution is 1 by 8. How many body center particles are there? 1. What is the contribution of the body center? We already discussed body center is confined to 1 and only 1, not shared by any other unit cells. So its contribution is 1. So this value is 2. So the Z value for BCC is 2. One more time. See on that board, BCC unit cell is given. Clearly where the particles are present also mentioned. The particles are at body corners and the body center. Body corner contribution is 1 by 8. Number of such body corner particles is 8. So due to 8 body corners, contribution is 8 into 1 by 8. And there is one particle which is confined to 1 and only 1, not shared by any other unit cells. So the effective number of atoms, that is Z for BCC, is 2. And last one. What is the effective number of atoms in unit cell of N-centered? N-centered unit cell. See the diagram. There are 8 body corners. So Z is equal to 8 body corners and its contribution is 1 by 8. Only 2 phase centers, for any phase center particle contribution is 1 by 2 only. 8 body corners, each body corner contribution is 1 by 8. Number of such body corners is 8. And there are 2 phase centers and phase center contribution is 1 by 2. So 2 into 1 by 2. So the Z value for end-centered cubic unit cell is also 2, like BCC. So this is, so what we completed so far, types of unit cells, lattice points, types of unit cells and effective number of atoms in different unit cells. Now coming to relation between A and R in different unit cells. So this is the most important part. What is small a? Small a is edge length of the unit cell. Small a is edge length of the unit cell. And R is the radius of the atom. Radius of an atom or whatever it may be, an ion or molecule, leave it. A, where wherever it is in solid state, wherever they mentioned small a, nothing but edge length, r is nothing but the radius of the particle. What is the relation between a and r in different unit cells? First one coming to simple cubic unit cell. See the diagram I shown. Say let it be, this is the face of the cube. In simple cubic unit cell, particles touch each other along the face edge. Means this is one particle and this is another particle. That is the most important thing. In simple cubic unit cell, particles touch each other along the face edge. From ear to ear, this distance is, from ear to ear, this distance is a. Why? Because it is the edge length of the unit cell. This is the radius of one particle from ear to ear, and from ear to ear, this is the radius of the second particle. If both the particles are identical, then A is equal to 2R. If both the particles are different, what it means, this radius may be different from this. If these two particles are different, the radiuses are different, then what in that case, A can be written as R1 plus R2. One more time listen students. In simple cubic unit cell, particles touch each other along the face edge. Means this is the way. This particle 1 and this is the particle 2. This from ear to ear it's called as the radius of the particle. Ear to ear is called as radius of the particle. The two particles may be same, the two particles may be different. And we all know from ear to ear it's called as edge length. And what we mentioned, edge length is A. Then A is equal to the radius of this particle plus radius of this particle. If the two particles are identical, then A is equal to 2R, or we can write this as R is equal to A by 2. Remember this student, this relation, because this we will use in calculation of packing fraction. And if the two particles are not identical, then the radiuses are not identical. Let R1 is the radius of the first particle and R2 is the radius of the second particle, then A is equal to R1 plus R2. That's what we mentioned, A is equal to 2R in case of identical particles. This is the relation between A and R in case of a simple cube. Now coming to FCC. Relation between A and R in the unit cell of FCC. That is the FCC unit cell. I think here what the important point, how the particles touch each other. One more time I will draw that face. Look at on the board. This is the face of the cube. In simple cube, particles touch each other along face edge, but in FCC, particles touch each other along face diagonal. This is face diagonal. And this is what is called as edge length A. This is edge length A, and we know that this angle is 90 degrees. So this is called as hypotenuse. According to Pythagoras theorem, the length of hypotenuse is A root 2. Because the square of this is equal to sum of the squares of these two. You all know that. So the length of the face diagonal is A root 2. In this, Particles touch each other along the phase diagonal. See students, this is important. This is one particle. This is another particle. This is another particle. See, this is what we may showed here. Here only the thing required where the particles touches. It is different in simple cube, it is different in FCC, it is different in BCC. In simple cube, particles touch each other along a face edge, but in FCC, particles touch each other along face diagonal. Now coming to this is R, radius of the first particle. From here to here, see this green ball, green atom. This is not the radius, this is the diameter, which is equal to 2r. And this is again r. So totally a root 2 is equal to r plus 2r plus r, nothing but 4r. This is the relation between a and r in FCC. So a root 2 is equal to 4r, or r can be written as a by 2 root 2. Remember this also will use in calculation of packing fraction. In case of simple cube, what we discussed in the last board, in case of simple cube, r is equal to a by 2. In case of FCC, r is equal to a by 2 root 2. Now coming to BCC. Relation between A and R in BCC. Now I will draw that cube. Say let it be, this is the cube. In simple cube, particles touch each other along face edge. In FCC, particles touch each other along face diagonal. In BCC, particles touch each other along the body diagonal. See, from point this to this is face diagonal. This is not by body diagonal. What is meant by body diagonal? Corners, edges of two opposite faces. This is body diagonal. And we all know the length of the body diagonal is a root 3. Now how particles touch each other? Just see, this is one particle. This is another particle. This is the third particle. See, in this diagram it clearly mentioned. From here to here is body diagonal, and we all know body length of the body diagonal is a root 3. Particles touch each other along the body diagonal, and this is from here to here is r, here to here is 2r, here to here is r. So totally 4r is equal to a root 3. R is equal to root 3a by 4. See, in simple cube r is equal to a by 2. In FCC r is equal to a by 2 root 2. In BCC r is equal to root 3a by 4. So this is what is the relation between edge length and the radius of an atom in 3 different unit cells. Only these 3 different unit cells are mentioned even in IIT Advanced Syllabus and NEET, which is there in intermediate second year as well as in CBSE plus 2 also. Now what is the next thing? Calculation of packing fraction. What's meant by packing fraction? One more time listen, students, this is very important point. In solids, particles are closely packed. Still there are some vacant spaces. Nearly 26 to 48% is vacant space in different solids. Because we discussed about that in that lattice points, in solids particles are present only some specific portions, remaining space is vacant space. Here we will calculate how much part is occupied by the particles and how much space is vacant in the different solids. What is meant by packing fraction? Packing fraction of a solid is nothing but volume occupied by total volume of the solid. Very simple, students. Packing fraction is defined as the ratio of the space occupied by the particles to the total space of that cube. What I wrote here? Volume occupied by V total. V occupied means volume occupied by an atoms or ions or molecules divided by what is the total volume. We all know total volume of the cube is a cube, where A is the edge length. Now what we want to calculate here, how much space is occupied by the particles in simple cube. The volume of one particle is 4/3 pi r cube. Volume of a particle, each particle is 4/3 pi r cube. How many such particles are there in simple cube? That's nothing but effective number of atoms. That is the reason why first we discussed effective number of atoms in different unit cells. What is the effective number of atoms for simple cube? Where the particles are present in simple cube? We all know particles are present only in body corners. The contribution of body corner is 1/8. Number of body corner particles is 8. So effective number of atoms for simple cube is 1. So number of particles in simple cube is 1 only. So we can write this as V occupied is equal to volume occupied is equal to number of atoms multiplied by volume of the particles. Number of particles multiplied by volume of the particle. We know that number of atoms or number of particles in simple cube is 1, and the volume of one particle is 4/3 pi r cube, and total volume is A cube, which is the volume of the cube, because A is the edge length. Then packing fraction in a simple cube is 1 into 4/3 pi r cube divided by A cube. Everything should be in a systematic way. See, in the first board we explained how to calculate the effective number of atoms. In the second we calculated the relation between A and R. Now we will use that relation A and R for simple cube. We all know R is equal to A by 2 because we are calculating packing fraction for simple cubic unit cell. Now I will substitute in place of R A by 2 here. So what is packing fraction? 1 into 4/3 pi r cube means A cube by 8, and the volume of the cube is A cube. We can cancel this A cube. This is 2 times. So packing fraction in simple cube is pi by 6. What is the value of pi? 3.14 by 6. So this value is nearly 5.2 something. What is this 0.52? That space only is occupied by the atoms or ions. Remaining is vacant space. So packing fraction 0.52, we can also write that as 52% of the solid is occupied by the particles. Then what is the vacant space? Vacant space is 48%. That's what I told. Though particles are closely packed, see how much vacant space is available in simple cube. Because particles are only at body corners. Remaining all three lattice points are vacant. So we will consider that as a vacant space. So the packing fraction or the space occupied by the particles in simple cube is 52% and 48% is vacant space. In the similar way, we can calculate the packing fraction of FCC and BCC also. Now I will explain how to calculate the packing fraction in FCC. See students, everything on the board. What we want? Packing fraction is nothing but volume occupied packing fraction is equal to V occupied by V total. And we all know V total is A cube. Now what we want? How much of volume is occupied by the particles? First you should know the Z value. How many effective number of atoms in FCC? We all know effective number of atoms is 4. How it is 4? Because it is FCC. Particles are at body corners. The body corner particles is 8 and the contribution is 1 by 8. In addition to that body corner, particles are present in phase centers. There are 6 phase centers and the contribution is 1 by 2. So the Z value for FCC is 4 and the volume of one particle is 4/3 pi r cube and the total volume is A cube. One more time listen students. Volume occupied by volume total volume is A cube. Volume occupied, volume of one particle is 4/3 pi r cube and volume of number of such particles is 4 for FCC. So volume occupied is 4 into 4/3 pi r cube and total volume is A cube. And you should know the relation between, you should substitute R in terms of A. In the last board we discussed R is equal to A by 2√2 in FCC. So simply substitute the R value in terms of A, will get the packing fraction 0.74. What it means? 74% of the space occupied by the particles. What is the vacant space in this? Vacant space is 26%. Packing fraction is 74% and vacant space is 26%. See, in simple cube, packing fraction is 52% and vacant space is 48%. Here the vacant space is less and more space in the cube is occupied by the particles. The maximum space occupied in different types of unit cells is FCC only. In FCC, 74% is occupied. Now coming to the packing fraction of BCC. Same here. If you can understand how to calculate the packing fraction for simple cube, it is similar in all the cases. No need to by head the things. You first go through the concept, then you can do anything. Same. You should know what is Z value for BCC. Z value for BCC is 2. What is packing fraction? V occupied by V total. And we all know V total is A cube. What is V occupied? Volume of one particle 4/3 pi r cube, and Z value for BCC is 2. Why Z is 2? Because in BCC particles are at body corners and body center. 8 body corners, so 8 into 1 by 8, and body center is 1, so Z value is 2. So number of particles is 2. Volume of one particle is 4/3 pi r cube, and the total volume is A cube. And here you should know the relation between R and A. R is equal to, in BCC R is equal to root 3A by 4. If you substitute that R in place of R, A root 3 by 4, will get the packing fraction. It will be nearly around 68%. And what it means? 68% of the space occupied by the particles. Then what is the vacant space? 32% is vacant space in BCC. So in simple cube, in FCC, in BCC, the maximum space is occupied by the FCC, 74%, and next to FCC, space occupied more in BCC, which is 68%, and next to BCC only simple cube, which is 52%. So this is what the calculation of packing fraction, students. So what the minimum thing required in solid state that we discussed, we discussed completely in detail all these subtopics. In the what are the subtopics that we discussed? One more time, just look at on the board here. What we discussed, lattice points. We discussed contribution of the particles, unit cell, and different types of unit cells, and after that how to calculate the effective number of atoms, and then the most important thing is relation between A and R, where A is the edge length and R is the radius of an atom or ion, and finally we calculated the calculation of packing fraction in simple cube, FCC and BCC. These three are included in your CBSE board, in your IPE board, IIT and NEET. In the next class, we will discuss the structure of ionic compounds and everything. Bye students.